no applaud required. But you know, we're up to last week, and this one is on retaining wall design and lateral earth pressure. So those are the two topics this week during the lectures. And lateral earth pressure is basically just a precursor to retaining wall design. It's kind of like how solid mechanics is a precursor to steel structure design or whatever. So retaining wall design is essentially just like applying theory so you can design a wall, right? Yeah, so as usual, on the left is a copy of my notes. For those of you who are new to this class, it's basically I go through the questions, I scroll through the questions a little bit quick sometimes, so if you like to have a copy of my notes up, you can write down everything. But with that said, I will be going through this workshop a bit slower. You'll notice there's only 2 questions. That's because this topic, there's a lot to break down. So I'd rather you guys understand 100% of 2 questions than like 50% of like 4 questions or something, you know what I mean? And yeah, if you'd like to join the mailing list, even though this is last week, that's on the right as well as you can give feedback to me. So basically, I'll record this workshop and then send it to you guys on that mailing list. Okay, so let's get on to retaining walls. So these aren't all the types of retaining walls. Down here I've included some embedded walls, but how I'd classify these first 3 that I've drawn on here is gravity walls. And they're essentially calculated more or less in the same way, but with some extra tricks and stuff. The idea is that all of them are based on resisting the lateral earth pressure from the active soil, right? So you gotta get, oops, one sec. Yeah, you're gonna have to get used to these terms. How do I? One second. Yeah. Okay. So, basically, lateral earth pressure is pressure from the earth, and lateral is just another way of saying horizontal, right? So it's basically horizontal stresses, similar to like hydrostatic pressure for water that acts on this wall. And so active earth pressure would be working like this way, for example, pushing the wall and causing it to be destabilized, whereas passive earth pressure would be like on this side, for example, it's basically resisting the sliding and overturning that can happen. Right, we'll get more into the types of failure in retaining walls in a second, but that's the general gist of it. So gravity walls use their weight force due to their self-weight to resist the sliding and overturning. Right. Same thing happens with a cantilever wall, except you also have to account for the soil that presses down on the cantilever wall, which helps to resist the sliding and overturning as well. It's kind of like in a library, you have a bookend that like the books sit on, and that stops the books from like sliding out or like toppling, right? That's basically what cantilever wall. And then yeah, we also have a gabion wall. So these are made out of like a steel cage, and then maybe not steel, but yeah, it's like some metal cage, and then there's rocks inside of it, right? And the weight of these rocks, it acts very similar to the concrete cases. But the idea is all of these work by helping to resist the lateral earth pressure through their own self-weight, essentially, right? Okay, so embedded walls, I'll touch on this a little bit at the very end, I think, because we're not going to be able to go through a question in this workshop for embedded wall designs. The idea of an embedded wall is that they're usually very light, so you ignore the self-weight of them, and you embed them very deep into the earth. So one example would be sheet piling, right? So sheet piling kind of has this, have you seen like the steel roofs that look like this? This kind of like shape? Yeah, so that would be sheet piling. And you stick that into the ground, right? And if you stick it deep enough into the ground, it's going to resist this lateral earth pressure. And then you have these two elevations, right? You have the elevation of the soil at the top and bottom. That's what you're designing a retaining wall for, right? Yeah. And so I should call this cantilever embedded. Not to be confused with the cantilever wall from up here, cantilever gravity walls. Cantilever embedded walls have a point of rotation which is beneath the surface of the soil at the bottom, but it's not quite at the very bottom. There's this point which it spins around, right? And anchored walls, they don't go as deep into the ground as your cantilever embedded walls, right? Which rely on this lateral earth pressure. This lateral earth pressure from the passive side is going to help resist the forces from the active side. But for anchored walls, essentially you have these things, these are called anchors, and they use like a cable pretty much to pull on the wall, and so there's tension in the cable, and that's going to stop it from overturning, right? The other thing to note is that in the questions, usually you won't get a diagonal anchored wall. Usually you might get something like this instead. It'll just be like horizontal. And usually this will be flat. You won't have like the sloped active earth on the other side, but anyway. So I'll talk about that again a bit more at the very end. Yeah, I would focus on gravity wall design for now. Okay. Oh, does anyone have any questions about any of these? Yeah. Okay. So basically, there's two ways to solve retaining walls for strength design, right? So there's the global factor of safety method and partial factor of safety method, which is actually the Australian code. So the Australian code, AS4678, whenever you see that in a question, that's an instant sign that you're going to be jumping to the partial factor of safety method. But if the question says use global design, oh, I just realized I am tampering with my main document. Let me just undo this, sorry. This one. Yes. Okay. Sorry. Where was I? So basically, yeah, here's the way you solve either one of them. So you have global factor of safety, and I'll also touch on the failure modes here. But these failure modes will also apply for partial factor of safety. It's just a convenient time to talk about it. So soil bearing capacity. This should sound kind of familiar, and the reason this sounds familiar is to calculate these, you actually use Hanson's equation, right, for a retaining wall. So we're not going to touch on this in this workshop, but if you're curious on what a question looks like for it, it's in this week's workshop for retaining wall design. Question 3. Question 3C has an example of how the soil bearing capacity would work for a retaining wall. But the idea is that if the retaining wall looks like this or whatever, that original shape, you have an inclined load and you consider it as a shallow foundation. Yeah, it's pretty rough. So you have to do all the I factors, all that stuff, if you remember from Hanson's equation. Anyway, we're going to be focusing on overturning failure and sliding failure in this workshop. So yeah, the idea is that for overturning failure, right, this is a cantilever wall, and this portion of the cantilever wall here is called the toe, right? This over here is called the heel. Don't ask me why. This is what it's called, right? But the idea is that at this corner of the toe, that's where we assume it's going to rotate from, right? Yeah, and for sliding failure, the main assumption is that we have to calculate the frictional force for resistance, right? The frictional force will determine our resistance, essentially, right? That includes, actually no, I'll talk about that more later. I don't want to overcook my explanation. But yeah, so this is how we do it in general. And the factor of safety is just our disturbing forces or moments over our resisting forces or moments, right? Okay. Cool. One more thing to note is that in the questions it'll say, is this an acceptable global factor of safety? The idea is if your answer sits between 1.5 to 2, then it's acceptable, right? That means you haven't over-designed it, but you haven't under-designed it so that it's not safe anymore, right? 2 to 4, that only applies for soil bearing capacity for retaining walls, but we won't see that in this workshop. Okay, does anyone have any questions for that, or is that okay? Right, we'll move on. Do you mind if I turn on the aircon? Because it stops like every hour. Are you cold or not? Okay, let's talk about partial factor of safety. So it basically involves everything I talked about in global factor of safety, but it's just a little bit different. And the main thing that's different is that you have to account for a bunch of scaling factors. So the way that I like to explain this is, some of you guys have done like steel design, concrete design maybe, right? The Australian standard for structural design, right? So this isn't quite geotech design. It basically makes you exaggerate the loads that are acting on your structure and reduce its capacity by a little bit as well, right? I'll give you an example. So, say you're designing scaffolding, right? Maybe it looks like this, whatever. And you're designing it to hold 3 tradies, okay? Say these tradies are kind of heavy. They all weigh about 100 kilos each, right? So when you're designing the capacity of that scaffolding, are you going to design it to hold exactly 300 kilos? No, probably not, right? What you'd probably do is you'd probably try to exaggerate the loading, right, in your calculations, and for the capacity of the scaffolding, you'd reduce that by some sort of factor, right? That's just how it works in Australian structural design. So we're doing a very similar thing. We're going to apply that concept, but we're going to do it for geotech design because it works a little bit different, right? So I've broken this down into A, B, and C. So A is the load factor. The dead load generally, okay, so dead loading and live loading, right? Let's just differentiate between these quickly. So dead loading is basically things that you can safely assume are always going to be there. And live loading are things that are going to vary. So like, for example, traffic, traffic on a bridge. You're not always going to have cars on a bridge. Sometimes there might be some driving on it, but then they leave and then whatever, right? So that'd be live loading. But dead loading involves like the self-weight of your actual objects, right? So in this case, we'll have dead loading for the concrete, for our concrete gravity walls, right? But you'd also have dead loading for soil, which, actually, yeah, that's all I'll say, just for those two, right? So it's to do with the unit weights of those materials, right? Live loading, again, would be from, for example, traffic, and usually it would come in the form of surcharge in our questions. And yeah, and also hydrostatic pressure, just have to keep that in mind. But the factors for hydrostatic pressure are just one, so you actually don't have to exaggerate them by anything. Okay, so soil reduction factors, what this one's about is reducing our material properties, like under exaggerating them by a little bit. So if you remember phi and c, it's friction angle and cohesion, right? The idea with that is that we're going to have to reduce these by some factor, right, in the Australian method. And these are just material properties from testing. We're just going to under-exaggerate them by some amount. That's what we're going to do. For classification factor, right, there's going to be like 3 classes, right? And class 1 is, it's very dangerous if this structure breaks, right, for this retaining wall. So say you have a retaining wall, and then on the high side of the retaining wall, there's like the column of a skyscraper, isn't it? In an extreme example, right? That would be class 1. Class 3 would be something that is like very minor, like there's not a lot of people nearby usually, so if it fails, no one's gonna die probably, right? So that's class 3, right? Okay, yeah, and then we continue on with our lateral earth pressure theory, specifically Rankin's theory, which I'll talk about. And we do a very similar process to what we do for global factor of safety, okay? And then at the very end, we have this equation, which is specific to the partial factor of safety method. But as you can see, we're going to use the classification factor at the very end, right? We're just going to either exaggerate or under-exaggerate whatever we get for our resistance by that factor. And then we check, tick OK. If it passes, yeah, you want the resistance to be greater than the disturbing forces or moments, right? Okay, does that make sense? Yeah? Alright, so here's what they actually do, like when we break it down, here's what it actually does look like, because it's in table form, right? So for soil bearing capacity, where we have soil failure, that's this first column. But again, that's not going to be in this workshop. That's going to be if they ask you a question to do with retaining wall design, and then they get you to calculate bearing capacity, use Hansen's equation, all that stuff. That's when you use that column. We're going to deal with rotation and sliding for the most part in this workshop. We're not really touching on serviceability for retaining walls, okay? Yeah, so you got your dead loads. I've talked about water pressure, just showing what I mean by water pressure here. But I want you to focus on dead loads and live loads, right? And this table, it's pretty confusing in terms of its wording. So here I've labeled 1, 2, 3 as these areas, right? So for dead load, area 1 is to do with the unit weight of the wall itself, as well as the unit weight of the soil, which like helps to stabilize the structure on top of the wall, right, on top of the base of the wall. Region 2 is the backfill, right? That's the lateral earth pressure, all this, right? Yeah. And region 3 is the dead load in front of the wall. So this generally acts as passive earth pressure, which helps to stabilize the wall from sliding and overturning, right? Okay, live loads. Let's talk about live loads. So, what is that? So sometimes you'll have live loads on top of your retaining wall, like in region 5 here. Yeah, I don't know. If traffic drives on the retaining wall, like this would be pretty unlikely, but if it is, that would be that. Actually, what would be more realistic is something like this. This region here, on top of the cantilever, right? That would also be classified as 5. So if you have live loading there, yeah. Region 6, this is your most common case where it's to do with the surcharge on the backfill. That's usually, yeah, like loading from traffic or whatever adjacent to the retaining wall on the higher elevation of soil. And then, yeah, same thing with 7, that's contributing to the passive earth pressure here. Like that, right? Anyway, oh, but you take it as 0 for live load. Well. Okay. That makes sense, more or less. Yeah, you got a question?
How do you consider the loads on top of it, like what contained in the soil, like for
Yes.
1 or spot?
Yep. Yep.
You consider the soil that's on top of the heel, but you don't consider the soil that's on top of the toe.
So the soil on top of the toe here, that would fall within region 3 actually. Do you know what I mean?
For that one as well, yeah, I consider like that little bit in front that's on top of the toe. I would consider that as
This one?
not the whole thing, but just like
Oh.
that bit on top of the toe.
Oh yeah, it's just because if you think of what I might do is I might just quickly draw. I always think of it as the bookend in a library. So these are your books, right?
Right.
And then here's your bookend that's holding the book and stopping it from sliding or overturning. That's basically what a cantilever is, right? So all this loading from the book squashes down on that bookend, and in this case, a cantilever wall, right? And stops it from sliding and overturning. So it's just, yeah, does that make sense? Like it's just grouped in that way. Yeah, sorry, I can talk to you in the back and like clarify that if you want. Okay, so soil reduction factors, they look like this. There's equations for them. And you know what I might quickly talk about? In my last workshop, when I talked about block failure, I want to talk about this a bit more because I actually realized where this came from. So when we're talking about a pile group with multiple piles, and then we're calculating for block failure, we're calculating the volume, that's that big block there, the volume of soil, right, and its failure mechanism. And it's based on this cohesion and adhesion, right? Well, we said that the cohesion was always greater than the adhesion, but these words, they're not just like random, they come from something. The idea is that the cohesion is to do with the soil's ability to stick to itself, right? Whereas the adhesion is the soil's ability to stick to another material such as concrete, okay? So when we're talking about the block failure of the pile group, we just take the value for cohesion, right? Because it's to do with the soil block failing based on like sliding with itself, right? Makes sense? Anyway, so how this applies to this week is in our soil reduction factors, we're gonna start seeing something pop up called delta. And delta is the friction angle of the soil, the adhesion friction angle. Okay, that's this one here. So it'll make more sense when we see the question and where it's slotted in, but it's to do with sliding, right? Okay. So it comes from this table. Yeah, it's based on these fill classes. Yeah, we'll see that in the question. That'll make more sense later. Yeah, we talked about structural classification factors already. It's to do with the purpose of the building. Okay, so with the lateral earth pressure topic, right, I've decided to mainly focus on retaining wall design, as I mentioned, but yeah, we're going to talk about Rankine's theory mainly. Coulomb's theory won't really help for retaining wall design, as far as I can see. I've included some notes for it, but they're optional to go over. It's basically like, don't at me if there's a Coulomb theory question in the finals, but I think it's pretty unlikely. All right. So let's talk about Rankine's theory. Basically, the idea is that for a retaining wall, let's just talk about a rectangular one like that, right? You have your, you know what? This is your active earth pressure, and that's your passive earth pressure, right? And so there's different formulas for either one. This is based on the Moore circle. I don't know where the derivation comes from entirely, but one is minus and the other is plus. And you plug it in, you get your coefficient of earth pressure for the active or passive case. And then you can plug it into these equations to get horizontal stress. So let's just go back to last week's content. This was pile design. Remember, for the case of sand, right, we had to calculate the vertical effective stress, and we could graph it like this essentially, right? We can graph it against the depth. When we are dealing with the horizontal graph, it's going to sit side by side with the vertical effective stress graph, except I'm actually going to draw the arrows in, and that's because it represents the direction of horizontal stress. For the vertical one, I wouldn't recommend drawing the arrows because it would be a bit misleading, but the horizontal distribution will actually correspond to what kind of pressure we'll be acting on, in our case, our retaining wall, right? And that comes from this formula. So the horizontal one is going to be a function of the vertical one, right? Multiplied by, well, not just multiplied by, but you're gonna have to plug it into this equation, right? Does that make sense? I think. Yeah. Okay. And one more case, if your soil on the active side is sloped, you might have a slightly different value for coefficient of active earth pressure. I've only seen this in the active earth pressure topic, not in a retaining wall design, but just keep in mind it might be something that comes up. I'm going to very, very briefly cover Coulomb's theory, but I don't think it'll be super important to learn. It's basically, you have a failure plane, assumed like slip failure plane, and you have two forces, P and R. They're both unknown forces, and P is from the soil to the wall, the force of the soil to the wall, and R is the force of the soil to the soil along the failure plane. And you can calculate these by drawing all these arrows to scale, right? Like these arrows being the force vectors, and then you literally use a ruler and measure them, and then you can get the, yeah, anyway. You do this, right? But they're not gonna make you do this in the finals, there's no way. There's literally no way. And there's also a passive case, which is slightly different to what I drew here was the active case. Yeah, anyway. Okay. So, am I going to touch on this? I'll touch on this at the very end, but let's do our quiz. What the fuck? Sorry. I'm gonna promote this on the side. Basically, we're gonna be running recap workshops for solids, steels, and geotech next Monday. So that'll effectively act as like another workshop if you want to come to that. I'll be the teacher for geotech. For solids and steels, guess who we have? We have Prash, best tutor at UNSW. So these will be really useful if you're doing steels, or if for some reason you're doing solids right now, come along to that as well. And it will be in this building, in room 109, so level 1 of this building, yeah? That'll be next Monday. So come along to that, it'll be really useful, it'll be really fun. Yeah. Like for the geotech portion, I'll be going over mostly like exam style questions and like working through those. So yeah. Alright, is anyone still joining? Alright, I'm gonna get started, right? Oh, okay, there we go. Alright, good luck. What's that noise? Aaron, is that you? Nice. Okay. So, I need this to be drilled into your head. The partial factor of safety method is the Australian design method. So that's AS4678 for retaining walls. All right. So just keep that in mind. So all three of these are correct, other than that weird one with the 9.81, whatever. So just keep this in mind. So in embedded wall design, we don't account for self-weight. I only briefly touched upon that, but that was at the very start. It's like, I would say, the main difference between the two types of design. In gravity wall design, we use the toe as the point of rotation, right? That corner at the very bottom of the toe. In gravity wall design as well, sliding failure will be a function of the friction. So we'll see how this plays out, and it can all be derived from like statics and like 1300 and all that stuff. Okay, so here we're talking about the dead load factors in that table for partial factor of safety method. It's basically just matching up all the definitions. Region 1 is going to be the dead load of the wall and the contained soil. So that's what it's talking about with the contained soil, right? All of that soil that's going to be like above the base, right? Oh, I think that's what you mean, Michelle, with that as well on the left. Just keep in mind, this is kind of how the regions are blocked out. So if it is a cantilever wall, it's only this region here, which is going to be for region 1. Okay, that's it. Right. That's like the contained soil. That's just what it's called, right? And then number 2 is the lateral earth pressure behind the wall. Yeah, that's whatever earth pressure is causing failure over here, right? And then the dead load of the field of this impermeable soil, that's the passive earth pressure, right? Very similar for live loads. Yeah, it's pretty much the same question. Okay, for sliding failure, right? We have here, I've just labeled 1, 2, 3, 4, 5, right? The idea is that for sliding failure, it's a function of the normal force, right? As you might be able to recall, force of friction, this function of the normal force, right? So that comes from the weight of everything from 2, 3, 4, yeah, everything above there, right? But we also have to account for the fact that region 1 is going to have this resisting force that's going to stop sliding as well, right? So it's 1, 2, 3, and 4. But as you see in the question, I think question 1 of the workshop, it sometimes just says ignore the resistance from the passive earth pressure. So that's this version. Sometimes it just says ignore that because it's like nearly negligible, right? In which case it would actually be 2, 3, and 4. But if it doesn't say that, I would still calculate accounting for the passive earth pressure, right? This class, like the bell curve, is a little bit more to the right than my 9 AM class. Maybe that just says something about the people who come to the 9 AM and 11 AM classes. No offense. But anyway, so yeah, here, obviously this is a joke, but like just promoting this again. Definitely come. I don't take maybe as an answer. You have to come basically. All right. Anyway, cool. So we're gonna have our break. How long will we give? 5 or 10 minutes? It'll be somewhere between 5 and 10 minutes, and then we'll come back. How about that? How's that sound?
Like, what if I just like reply to the email? It's like, why didn't you discuss it? So do I do that or do I not? Okay. Well, he just has it.
I'll email I actually got an email from his like company or whatever like I got invited to an event.
You want
for being like
sponsorship?
the top 5% of his users.
I see.
Because his content creators.
Yeah.
Wow. I've only made like 10 of these.
That's crazy.
That becomes sponsorship.
Yeah. But it's like you were invited to a lunch with Zeus content
Where was it?
creators. I don't know. I think they're Australian. But I don't know where it was. Like,
You should invite us.
plus one. Yeah, there's a lot. Like, the reason why these options I tend to be like multi-choice is just like a lot of the options are like so like it's fine, like I low-key think, like I didn't look into too much, but I low-key think that might be a look because it says it's free for like all the shit. So I don't know if I was supposed to see a bunch of people doing stuff. I also don't want to especially because my friend has it, so like
He's like, you want to start doing yourself for a little bit.
What
I think you decided first.
Yeah. That's crazy. Yeah. I moved. Actually, the gap here. You actually discussed. I know you want to see my class, like fellow strength. Like, it's like a person. I would go dating to Yeah, I know. Even when I moved to Sydney, this was no one would want to try to be here. Kind of like a newer, it looks like voluntary stuff. Yeah, you can print out whatever. Usually it's like it's actually
Yeah, what do the next day?
Alright, we'll get started again. Alright, let's get back to it. So here's the first question. So just give this a quick read. I'll pull up my notes. But what's the first thing that stands out to you? Retaining wall. Yes, exactly. AS 678. Oh, 4678, right? Yeah. We're going to be using the partial method in this question, right? Okay. Let's read the question. There's a bug on the table. Okay. Let's read the question carefully. So it's a gabion wall, which is just a type of gravity retaining wall, essentially, right? But it's a bunch of rocks stuffed in a cage, right? Yep. And okay. So the next bit of important information is that the wall is near a minor road and there's no buildings nearby. So that will give you some more information about which kind of factors we're going to be using, right? And then the next thing is the soil properties. So we have the unit weight of the soil, we have the unit weight of the gabion, right? And then we will have a bunch of these soil properties. We have that the cohesion friction angle is 35, the adhesion friction angle delta is 25, and we have the cohesion, because of sand, is 0, right? Here we go. So we need to apply all this information and use Rankin's theory and evaluate the stability against sliding and overturning, okay? So this is going to be strength design. Alright, so, one more thing I missed, sorry. A live surcharge of 5 kPa is applied to the soil behind the wall, yeah? So I've just drawn it on the diagram, but in the original diagram that wasn't there, so you're going to have to read the question carefully. And it's uncontrolled backfill as well. That's kind of important information for the factors as well. So I'm going to be scrolling. So if anyone needs my notes, the QR code, all that stuff, yeah, just let me know. Okay, so we're going to be using the load factors, right? So we're dealing with rotation and sliding, yeah? So we're going to look at this column. And in terms of the rows, we're going to have to decipher what all of these things are categorized in. Okay, so let's start with the surcharge. That's the live load at the top. right? So we look at live loads, and from the live loads, which one's that going to be? Sorry, it's kind of hard to read. Which one's that going to be classified as? Oh, sorry. Like the surcharge load up here. What type of live load is that from the load factor table? It's this one. So it's the backfill. The backfill refers to the soil like at the higher elevation, essentially, right? That word comes from how it's installed. Backfill is like you kind of get soil from another site or whatever and then deliver it on site and you level it out from that, right? Okay, so that's our live load and the factor will be 1.5, cool. For our dead load, so we're gonna have two dead loads and they're gonna be corresponding to unit weight, right? So we have the unit weight of the gabion, and then I don't know if I'm pronouncing that correct, by the way, but yeah, I'm gonna call it gabion. And the unit weight of the soil, right? And that soil is applying like the lateral earth pressure, all that stuff, right? So that's gonna correspond to the dead load of the wall, right? And the dead load of the earth pressure behind the soil. That's those numbers there, right? Okay, so here's what we're gonna do. We're gonna call all of those values, whatever value, and then star, or like little asterisks next to it. That's gonna imply that we've already factored it, okay? So we're gonna multiply it by 1.5. That's the purple one there. And that's going to be 7.5 kPa. So that's our factored surcharge, right? Our factored unit weight of soil is going to be the unit weight of soil multiplied by that factor from that table. Right? Our factored unit weight of the gabion is going to be that multiplied by 0.8. Okay, oh, sorry. Let me plug in these numbers. By the way, if I didn't already mention, I'm going to be going very slowly in this workshop and explaining everything as in-depth as possible, including like 1300 like statics. Yeah, very bare bone basics. All right. So sorry if it kind of is too slow for you, but anyway, this one will be 17.6 kilonewton per meter cubed. Oh, that's based on the feedback, by the way, that I got from the other things. They said in week 5, I was going too quick. I was explaining like the more Coulomb like criteria or whatever. So I'd rather explain fewer questions, more in depth, than more too quickly. Okay, so with soil reduction factors, we're doing strength design, and we're dealing with sand, right? And we have a cohesion of 0, so we don't actually need to look at this row. This row is only like a scaling factor for the cohesion component. So we only need to look at, this is capital phi, u, phi. Okay, let me write that up. That's our scaling factor for friction angle, right? And we're also gonna apply the same one for the friction angle for adhesion as well as cohesion, yeah? And this is drained analysis. So up here was the drain analysis stuff, down here is undrained analysis, yeah? But yeah, sand, drain analysis, yeah? Okay. So we're dealing with uncontrolled fill. This was described in the diagram in the question, right? Uncontrolled fill of sand. So we look at it like this, we go over, our value is going to be 0.75, okay? Yep.
I know I explained uncontrolled column, but I think that row.
Sorry, can you say that again?
Like, it's uncontrolled unfolded set, so we know it's an uncontrolled fill column, but how do we know what which row to use?
Yeah. Okay, so basically, we're not dealing with serviceability design in this topic, essentially. That's to do with settlement, right? Strength design is like whether it's safe, like whether it's going to collapse. So first, that's why we're dealing with the strength row, okay? And then when we go into this row, that's because we're dealing with just the friction angle. We don't care about scaling the cohesion because there's no cohesion, right? And this bottom table is the undrained analysis portion of it. Yeah. Okay, so we're going to scale everything. Here's how it'll look. We're going to replace this by 0.75, right? We're scaling both the cohesion friction angle and adhesion friction angle, yeah? And that's going to be that with a star next to it. Plugging in the numbers, this is going to be 35 degrees and 25 degrees. That's from the question. Resulting in these numbers, right? So this is just our factored angles, right? Okay, next, the structural classification factor. The question describes that the purpose of this retaining wall is that it's on a minor road, it's next to a minor road, and there's not many people nearby. I think it said like, there's no buildings in sight or something like that, right? Basically, this means it's class 3, and that means, so in the table, I haven't included this table because it's such a small table that, yeah, it's 1.1 basically. What that means is at the very end, we're going to be exaggerating our resistance by a factor of 1.1. Yeah. Here I've drawn a free body diagram of our whole, basically we have a cross section of this retaining wall. The retaining wall could span for quite a while, but we've just taken a cut, right? And we're looking at, we're looking at it from the side. I've just noted down essentially the unit weights that we've scaled and the surcharge which we've scaled, and just drawn the dimensions again. I'll talk about W later. W is the self-weight of the gravity wall, right? Okay, so just have a think about what the vertical stress distribution will look like. This is very similar for vertical stress distribution of the piles that we talked about last week, except it'll be different, right? All right. It's gonna look like this. So when I was solving it, I originally thought it was going to be a triangle, just from habit of the other topic. But in this case, we have surcharge, right? This surcharge is going to result in a starting value of 7.5. So we're going to be dealing with a trapezium, right? Trapezium shape. Okay, so that amount on our diagram is going to be 7.5 kPa, right? So now we have to add on a certain amount, making it go more to the right, essentially. So the formula will look like this. Oops. No. Formula will look like this. 7.5 plus, this is our factored unit weight of soil, right? Of active soil. That's going to be multiplied by 2 meters in depth, because that unit weight is going to compound and then increasing pressure as you go deeper into the soil, right? I'm going to move that across a little bit, give myself some space. So that right there is 52.5, right? Okay, here I'm gonna be graphing right next to it the horizontal effective stress. Okay, and here I've included just this part of the formula, but it essentially keeps going and has like a component for cohesion. but because we're dealing with sand, I've just excluded that portion because C is 0, right? So I'm not going to write that in. But here's where Ka comes in. That's that number that we calculated a second ago. Wait, did I even mention that? Alright, we plug in 27.7 degrees as our scaled phi value. Okay. Yeah, that's where 0.37 comes from. So that's our coefficient of active earth pressure, right? Once we've multiplied that, we essentially take this value, right? We take that value and multiply it by 0.37, right? That's going to be this value here, 2.775 kPa, okay? And to get this bottom value, we have to multiply 52.5 by the coefficient of active earth pressure, right? 19.425. And again, I like to draw the arrows for lateral earth pressure, sorry, the arrows for the horizontal effective stress, because that corresponds to our lateral earth pressure essentially, right? So like how this all works out nicely is that this will be the earth pressure acting on the wall like that. Does that make sense? Yeah, that's why I've decided to draw it like this. I think it's a really clean format. So yeah. Next, we're going to be talking about W. W is the self-weight of the retaining wall, right? And yeah, from physics, center of mass, right? You take the center of mass of an object. In this case, it's going to be in the very middle, like in terms of the shape, and that will be your weight force, right? And it acts downwards towards the core of the Earth. Yeah, that's what we're going to be doing. But instead of mg, we're going to do it in terms of this. This is the unit weight of the gabion. And we have to multiply it by this cross-sectional area. That's this area here. Okay? Once we do that, we're going to be able to get the weight force of the gabion per meter run. Okay? It's 35.2 kilonewtons per meter run. There you go. That's W. Okay, so this is just for context. You don't have to draw this. In fact, I recommend you don't draw this every time you do a question, but it's just so you know what we're talking about. Overturning, yeah, is to do with like the moments, I guess, about that point of rotation, O, which we're going to take as the corner of the toe, right? And this lateral earth pressure is going to cause this to spin and overturn. So that's what we call a disturbing moment, right? And what's going to resist it is, you know what, whatever, W, right? And because W is causing a clockwise spin, right, on our cross-section diagram here, about point O, that's going to be our resisting moment, right? Does that make sense for overturning failure? That's how it works. Okay, so for overturning failure, we have to calculate the magnitudes of the forces as well as the lever arms, right, from all our forces to that point O. So that's point O here. And we have this force W, this force F1 and F2. So I've broken up the lateral earth pressure into two forces because it's a trapezium. And yeah, if you don't want to do integration, I would recommend breaking up trapeziums into like a rectangle and a triangle, because it makes life a lot easier, right? Okay, so let's calculate the lever arms first, okay? The lever arm, let's just do a little quick 1300 recap. Let's talk about W first. So W is the weight force, right, of our gravity wall. What I've highlighted in blue is the line of action. So the line of action spans infinitely in both directions from that arrow, right? And the idea of a lever arm is from our point of interest, right? In this case, point O, the lever arm is the perpendicular distance from the line of action of our force to our point O, right? So that's going to be our lever arm there, yeah? In which case that is going to be 0.5, okay? We have to think about these lines of action as well for F1 and F2. Right, so we find the lever arm. For this one, it's going to be 1 meter, right? Because it's a rectangle for F1, so it's going to be half of that height, right, of the wall. For F2, for a triangle, the lever arm is at 1/3 from the big side of the triangle, okay? So what would that be? If we're doing 1/3, 1/3 of 2 meters is 2/3, like you said. That's all our lever arms sorted. Next, we're going to do the force magnitudes again. So for force 1, all we have to do is take the area of this rectangle, right? And so this lateral earth pressure, if we scroll up, actually no, I'll write it here. Yeah, so for this rectangle, this was 2.775, right? And in terms of its height, 2 meters, right? Once we calculate that area, that's going to be 5.55 kilonewtons. We only care about per meter run, yeah. So we don't care about into the page or anything. It's just the area of the rectangle, yeah. F2, triangle. Meters. Okay, this here is going to be 19.425 minus 2.775. Right, that comes from this whole, that stress minus that stress. Right, so it's that difference here. We're doing in red. That difference here is going to be that side of the triangle. Yeah, take the area. Make sure to account for the half because it's a triangle. These are 16.6 kilonewtons. Sorry if I'm going too slow. I'm going really slow here. It's from like first year basics, right? But yeah, I'll promise I'll speed up like for the next example. All right, all make sense? So now we're going to do the disturbing moments and resisting moments, okay? So the disturbing moments, we're going to group together everything which gives us a counterclockwise spin about point O, okay? So that's all the forces times the lever arms. In this case, we only care about F1 and F2. F1 and F2 is those two blocks of the lateral earth pressure, right? And we're going to multiply it by that lever arm. So the lever arm for F1 about point O is 1 meter. The lever arm for F2 is going to be 2/3 meters, right? Plug in what we calculated already for F1 and F2. Yep. And then that gives us 16.62 kilonewton meters, right? Because we're calculating a moment, right? Yeah. So all we did was group together the counterclockwise moments, right? This is also called S star. When we're dealing with the Australian notation, that would be S star, right? So for resisting moments, we do the opposite, which is we group together the clockwise moments, okay? So these will give us resistance. We'll call this R star. And if we look on this diagram, which forces are going to give us a clockwise spin? About 0.0. Just the weight. So the weight is the only one that's going to give us a clockwise spin about 0.0, right? And then we multiply that by our lever arm, which was 0.5. Get it? That's 35.2. That gives us 17.6 kilonewton meters, okay? Cool. So before we do our final check for overturning failure, I've decided to do the checks together at the end. We're gonna calculate for sliding failure. Right, so sliding failure, there's just like a few things to note. Disturbing forces are calculated the way that you probably think they will be. That's just the sum of the forces going to the left in this case, right? This will be our S star in the case of sliding. So we literally just group together F1 and F2, right? And what numbers are these? These are 55.5, oh sorry, 5.55 kilonewtons, 16.6 kilonewtons, giving us 22.2, an S star value of 22.2, okay? Okay, for resisting forces, this will work slightly differently. So this will be based on our frictional force, okay? So, let me just draw a quick free body diagram. So we have our active earth pressure, and our friction is going to be acting along that surface at the base, right? Acting to the right, call that frictional force. And if you remember from like 1300 or physics, to calculate this, we need to calculate W. W's, you know, our weight, mg or whatever in physics. And we calculate our N, right? Since this whole thing is in static equilibrium moving up and down, like it's not moving up and down like that, I'll just do this whole thing. Basically, what I'm trying to say is that N is equal to W, right? That's the first step. The next thing to note is that we're in static equilibrium for our frictional force as well, because we're not, how do I say this? We haven't moved yet, but we're calculating the maximum force it gives in friction before it starts moving. Okay. So, what this means is that we have what do you call it? FF minus F active, yeah. So anyway, yeah, whatever. I'm just gonna stop deriving it. Basically, the idea is we do this. Everything moving to the right, we're going to group together as the resisting forces, and this is going to be equal to our static friction constant multiplied by our normal force, okay? But as we discussed, normal forces is W, right? And static friction force, as I mentioned briefly at the start, in this topic in geotech will just be tan delta star, okay? That's it. So that's our adhesion friction angle, okay? We can plug in W, which we calculated, and from the question, from the question we were given some delta value, we've scaled it, and then that value we plug in, 19.28 degrees. So we get 12.31 kilonewtons, and that's the force going to the right, yeah? So now we're going to do our check for overturning. So if you recall at the start of the question, our structural classification factor, that was 1.1 because of minor road. So we do 1.1 times, for overturning, that value was from up here. R was this value. So we're going to do 17.6 kilonewton meters. It's greater than 16.6 kilonewton meters. So it basically passes that check. Right, good. Okay, for sliding, we do a very similar thing. That's going to be 1.1, and then we're going to multiply it by 12.3 kilonewtons, okay? So, yeah, 1.1 times, that's basically our frictional force, right? Anyway. Our frictional force, and then S was the lateral earth pressure force acting to the left. But, as you can see, this one does not pass the check, and therefore it fails. So, anyway, that's our question. So, our wall works for overturning, but it fails in sliding. Okay. Does anyone have any questions? Yeah, Russell.
I remember you wrote like when you find the active soil, you did per meter run, like the bracket here. When you have to do that bracket per meter run, like would you do it like for checking the soils and?
Actually, almost everything is per meter run, because we're analyzing just a cross section, right? So let me just draw this out in 3D. So imagine you have that wall. This is our rock wall. It's a cage, right? And it could be very long, you know, it could be however many meters in length. And then that's our high elevation of soil. That's our lower elevation of soil, right? We're actually just taking that cross-sectional cut to do our free body diagram analysis. So actually almost all our calcs are per meter run. I've only included bracket per meter run, like for my explanations to you guys. You don't actually, I mean, you can include it, you could not include it, but as long as your numbers are right, then it's fine. Yeah. Yeah, sorry, I don't really have a clear answer for that question, but yeah, basically most of our calcs are per meter run, essentially. Does anyone else have any questions for now? Alright, let's move on. Okay, so this question, the important thing about this question is that we're dealing with clay now instead of sand. Okay, but what's interesting about this scenario, it's kind of a bit more of an uncommon scenario, is that the clay is sealed so that no water can enter the backfill. So even though we're dealing with clay, we're actually doing drained analysis, okay? And so we'll be doing all the material properties stuff related to drained analysis. So that's like C dash and fire dash, all that stuff, right? So normally when we're dealing with undrained clay, we take the friction angle as 0, right? So this is where it differs. This will be slightly different since we're dealing with drained clay. Yeah, note that the surcharge is 10. Oh, actually it's already written here. Yeah, surcharge on the top is 10. And if we read part A and B of this question, part A says, determine the factor of safety against overturning for the wall. It doesn't specify the Australian standards or partial factors method, but part B does say to use it, okay? And it's still against overturning, right? So, you see where this is going? We're not going to do our sliding checks, we're just going to do overturning checks in A and B, but one's going to be global factor of safety method, and then part B will be partial factor of safety method, okay? Okay, yeah, so let's move on. So because we're not dealing with the partial factor of safety method, we're actually going to jump straight ahead to Rankine's theory, straight away. That involves calculating the Ka factor, that's the coefficient of active earth pressure. One thing to note, I think it says, Yeah, here it says it. Ignore any passive soil resistance in the front of the wall. You know what I mean? So we ignore all of this passive earth pressure. That's what I was talking about earlier. So we only have to calculate the active earth pressure constant, okay? Phi we just plug in, this is 30 degrees, and we get 1/3, okay? For our vertical effective stress, looks like this. So a charge of 10, yeah, and then 10 plus the unit weight, 18, times 4 meters of depth, that's how much it increased by. Do that purple. Yep, so that's our distribution for vertical effective stress, yeah? Next, we're going to calculate this formula. That's 1/3. That's 1/3 as well. Keep in mind, this portion is relevant when you do have cohesion involved, okay? Our cohesion value was 5, right? So the only thing that this graph will be varying by is vertical stress, yeah? So essentially, in a calculator, we plug in 1/3 multiplied by this value here, 10, right? Minus 2 times 5, square root, 1/3, all that stuff. And then our stress distribution is actually going to look like this. Yeah, because we subtracted some amount, right? And then this value here, 2.44, negative 2.44 rather. Here we're going to get 21.56. Yeah? Okay, I've got good news and I've got bad news. The good news is that we don't consider the tension zone. That's that negative region of lateral earth pressure. We don't consider it. The bad news is now we have to use similar triangles, okay, to work out this height. We're going to call that x. And we're going to call this 4 minus x. So 4 comes from the fact that this wall is 4 meters high, right? And then that remaining height is going to be 4 minus x, right? Okay, so how do we do this? I've done it on the right here. It's very similar to shear force diagrams and stuff in 1300. What I like to do is this triangle is equal to this triangle, okay, in terms of geometry. The rise I consider as the stress value, that peak stress value of that triangle, 2.44. I'm going to do it, the maths will work out if you do it positively, okay, so keep that as a positive number. And the run is 4 minus x, okay? The rise of this triangle is 21.56, and the run is x. Get it? So now it's just a matter of solving for x, right? We cross multiply. Like that, and then, yeah, just group like terms, all that crap. So x is equal to this. Giving us, move this across, 3.59 meters. Okay. So you can do a sanity check. If this number is greater than 4 or less than 0, you've done something wrong. Okay, so it has to be between 0 and 4 meters, yeah, because it's a portion of that 4 meter depth. Okay, so I've written it here, right, and I've excluded the tensile triangle, tensile stress distribution. Okay, so now we have kind of like, this is the setup, right? We have our point O, we have we've broken this retaining wall into rectangles essentially, right? So there's two concrete parts. Let's call it W3, sorry. So W2 and W3 will be concrete. W1 will be soil, right? And I've also drawn the lateral earth pressure to the right of it. Okay, and that triangle goes up from the base 3.59 meters. Yeah. All good? Yeah. All right. I've drawn the same thing again on the left here, but I've just given myself more space to write everything. So Q is basically the soil surcharge of the soil contained above the retaining wall, okay? And it's a resultant force, right? So here we do 10 times that distance there to get Q, okay? So what I'm gonna do is I'm gonna split up all the, I'm gonna split up the geometry. This will probably make it a bit more clear. So that's 3.6 there, that's 1 there, okay? And we want to find the lever arms of all these forces, right? Because we're going to do overturning. So we need that distance from O to W3, for example, O to W2, O to W1, and O to Q, etc., O to F, right? So we need all of those distances. So for W2, that will just be 0.2. For W3, that's 0.7. Because we're taking half the distance of that base, right? W1, you add on 0.4, and then half the distance of 1. Oh, didn't draw that very well. And half the distance of 1, right? Because it's the soil contained above the retaining wall. So essentially that's 0.9. Okay. To get this lever arm for the lateral earth pressure, that's going to be 3.59 divided by 3, because it's 1/3 from the big side, yeah? I think that's it. Yeah, okay. Force magnitudes. So we're going to calculate it for Q, we're going to calculate it for F. Right, so as I alluded to earlier, Q is going to be our surcharge of 10 multiplied by 1 meter. 1 meter is the amount of soil contained above that retaining wall, right? Or above the cantilever portion of the retaining wall. The heel, yeah, that's what I was looking for. Okay, F is our lateral earth pressure, okay? So it's literally the shape of that triangle. So half times base times height, yeah? So this is the base. This is the height, 3.59. We have 38.7 kilonewtons. Okay. We still need to calculate W1, W2, and W3. Keep in mind W1 is to do with the unit weight of the soil. W2 is to do with the unit weight of the concrete, and so is W3. Okay. This value was 18. This value was 25. So is this one. Alright, so visually you can think of it like this. We have to multiply the unit weight by these areas. So for W1, we need this block of soil, this area of soil. Yeah. W2, this area of concrete. W3, this area of concrete, okay? So for W1, it's 3.6 times 1. W2, that's 3.6 times 0.4. And W3, 0.4 times 1.4, okay? I'm going to highlight that. W1's that. W2's this. W3's that. Giving us 64.8 kilonewtons, 36 kilonewtons, and 14 kilonewtons. Okay? Got it? Yeah. This is all per meter run and all that, right? I've just not included it. Okay. So, disturbing moments are going to be our counterclockwise moments for this case, right? So we just group together all the counterclockwise moments together. That's the force of the lateral earth pressure times its lever arm. Found was this 3.59 over 3. That's this value here. The value for F we found was 38.7 kilonewtons. Okay, giving us 46.3 kilonewton meters. Okay, let's do the same thing, but in the other direction, grouping together the resisting moments that are going clockwise. So essentially, the forces that are causing a clockwise spin are going to be W2, right? W1, W3, and Q as well, right? The surcharge of the soil contained within the heel, right? So all the lever arms go like this. And we calculated these forces. Like that. Giving us 84.32 kilonewton meters, okay? Keep in mind we're still doing the global factor of safety method, right? So what that means is the factor of safety we have to calculate is the resisting moment divided by the disturbing moment, okay? Just like that. This gives us 1.82, okay? So if you recall, the acceptable range for overturning was between 1.5 and 2. So this is okay. The idea is that if it's greater than 2, you're over designing it, you're spending too much money on like concrete materials, all that stuff. If it's less than 1.5, it's not safe. It could collapse, right? Yeah, does that make sense, guys? We're not done yet. We've got part B to go. Same question, but we're gonna, I'll just show you how the partial factor of safety method changes things slightly, okay? So essentially, in the question it's described that the live load is due to traffic loading, okay? Oh, sorry, the surcharge is due to traffic loading. So, you know, it's like a live load essentially, right? Let's look at the table. We're dealing with rotation and sliding, yeah? And so for live loads, specifically the traffic live load, okay, we're dealing with the backfill behind the wall. And so we get 1.5. Very similar to question 1. For the dead load, okay, the dead load of the wall and contains soil, and the dead load of the earth pressure behind the wall give us 0.8 and 1.25 accordingly. Okay, so one's actually a reduction factor and the other's like a scaling factor. Okay, so let's talk about one thing at a time. So I'm going to talk about the surcharge first, yeah? So the scaled surcharge is going to be 1.5 times whatever surcharge we were given. So Q star is going to be 15 kPa, okay? Next, let's talk about the concrete. So gamma star of the concrete is a resisting dead load, okay? And so it's actually reduced, okay? You want to, again, from the scaffolding example, you want to under-exaggerate the capacity of our resisting forces, yeah? So we multiply that by 0.8, giving us 20 kilonewtons per meter cubed, okay? For the soil, this is where it gets interesting. We're actually going to have two values. Okay, we're going to have 0.8 times 25, as well as 1.25 times 25. 14.4 kilonewtons per meter cubed, and 22.5 kilonewtons per meter cubed. And the reason for this is this, this exaggerated unit weight value for the soil is going to be used in our calculations for the active earth pressure. This one. Yeah? Here I've drawn it on the side here, in this zone, yeah.
Wait, is it 25 or? I'm assuming you're not on the right there. It's like
Oh, sorry, I keep saying the wrong thing. So if I write down something, it's probably correct, but if I say it and utter it wrong.
The number like 14.4 is correct to 5. I think that's probably 5, but it shouldn't be 25. It's sort of something else.
Wait, 0.8 times. Oh, yeah, no, sorry, I wrote down the wrong thing. Oh my days, I'm sorry. Yeah, sorry, that's 18. Okay, that looks more right, yeah. Sorry. 0.8 times 18. Yeah, that's the right one. Thank you. I wouldn't have caught that. Okay, so yeah, so for the active soil, right, that's what we use for our lateral earth pressure distribution calculations. For the soil contained above the cantilever retaining wall that we use to calculate the weight force, that's going to be a resisting load of moment, right? So we're going to under-exaggerate that by a little bit. Anyway. So, next is soil reduction factors. Just in the question, we're given that it's fill class 1. So I actually haven't included the entire table here, it keeps going, but just for the sake of space, I've decided to only include this corner of it. And unlike last time, we're going to be taking both these rows, and the reason for that is that this top row applies to our friction angle, and that bottom row applies to our cohesion, in which case, because in our case we have both, right? And then lastly, actually, you know what, I'll show you what that looks like. So on the left here, that's our C star and phi star calculations. Yep, we just scaled down our C star and our phi star values. Okay. So these values were from the table. That's these ones. It's the other way around. In my writing. Yeah. Okay. So the structural classification factor. This question is non-specific. I'll tell you how you deal with that at the very end. Okay. So Ka we calculate, except this time we're going to plug in our our factored friction angle, yeah? So that's that value on the left here. It's 28.7 degrees, giving us 0.35 as opposed to 1/3. Next, we're going to calculate the vertical stress distribution. So our surcharges increased from 10 to 15, and the base here, we're going to do 15 plus this value here is our exaggerated soil unit weight, right? So the active lateral earth pressure, right? That gives us 105 kPa. Okay, that's that point here. Okay, and so now we plug in everything. This gave us 0.35 in the square root, and our C value is 4.5 instead of 5 now. So everything will just give slightly different values. Here, this is negative 0.074, and this is 31.43. Okay, so as you might be able to tell from the difference in these numbers, this isn't to scale. Negative 0.074 is really small compared to 31, right? So how it will actually turn out when you calculate the similar triangles is that x is 3.99, which is pretty much 4. So you can just pretend that the tensile zone never existed to begin with, and that the distribution is actually triangular, like that, right? As in, like, there's always triangular, but you know what I mean. It's a big triangle the whole way, yeah. So this is kind of important. For a partial factor of safety method, do not include the live load for the cantilever portion for the heel, okay? This is because it's already accounted for in our previous design values. So yeah, it's just a difference in the method, okay? That means we don't calculate the Q force like we did before, okay? Just completely disregard that. Okay, and like before, we're going to take the lever arms. Oops, sorry. Let me just fix this up. That was 1 meter. This was 0.2. This was 0.7. This was 0.9. This is now 4 on 3 meters instead of 3.59 on 3 meters. Yeah, and that's it. Okay, so now we calculate the new magnitudes. This is half. We'll do the area of the triangle, so this is the base times the height. For the weight, we do the unit weight, the scaled unit weight of soil and concrete, multiplied by that area that we can see, right? 3.6 times 1, 3.6 times 0.4, and 0.4 times 1.4, giving us 51.84 kilonewtons, 28.8 kilonewtons, and 11.2 kilonewtons, okay? So now we're going to calculate the disturbing and resisting moments, bringing us towards the end of the question. Grip the counterclockwise moments. I've stopped doing things in color code in the interest of time. And same thing, grip together the clockwise resisting moments. We call that R star and S star. So these are terms specific to the Australian code. Yeah, this is the partial factor of safety method. W1, 51.84, W2, 28.8, W3, 11.2, giving us 60.256 kilonewton meters. Okay, so now we plug everything in finally. This was, actually, we won't talk about that yet. This was 60. This was 83.813. Yeah, okay, so basically what this comment in blue says is even if we're generous and give phi n a scaling factor of 1.1 based on class 3, this wouldn't satisfy, right? So the number on the left is too low compared to the number on the right, and therefore this whole thing would always fail. Yep, okay, that brings me to the end of my class. Thank you for joining me in these workshop sessions, and hope to see you in week 11 on Monday if you decide to come to that. Yes, so just a few tips for your exam. Because it will be in person and on pen and paper, I recommend that you try revising using pen and paper, you know, because it's a lot faster. So like, at least for me, compared to when I do everything digitally, doing things on pen and paper is faster, and the aim of the game for your exam will probably be time, right? It's trying to do things as quick as possible because you might find yourself running out of time. So yeah, good luck. I'll be up the front as well if you have any questions, but yeah, that's it.